Hi everyone, welcome back to the workshop, and today I've got something a little bit different. Dan from England was very kind to donate this Keithley 440 digital picoammeter to the channel. Now it's not actually faulty, but it did present a problem to him in terms of calibration. Now what is a 440 digital picoammeter? Now looking at this large range selection switch here, this ammeter can go from milliamps all the way through microamps, nanoamps and picoamps. And it's picoamps that presented a problem in terms of calibration. And today we're going to try and see if we can do something about that. Now it's a simple enough unit, but what will catch your eye is this absolutely gorgeous Nixie tube display here. You've got 4 Nixie tubes in behind here, which just gives it an absolutely lovely display. You've got 3 Nixie tubes here that are capable of displaying a number between 0 and 9, and you've got a 4th one here which is off at the moment, which can just display a 1. Over at the left hand side, I think that's actually just an LED, or not an LED, a light. Because this unit dates from 1974. That's what's in the manual anyway. This unit's 50 years old. And having played around with it for the past few hours, I can promise you it's well up to the job of what it was designed to do, even at the picoamp scale. Over at the right hand side, we've got an operate zero check switch. I'm in the operate mode at the moment, meaning if I feed in a current, it will be displayed. We've also got a zero check position there. Now, as you can see, the display jumped to 0 or thereabouts because you've got a small potentiometer down here that you can adjust just to trim that to 0. You've got the input connection here. It's a PL259 style socket. So I've just made up a PL259 to BNC adapter for the purposes of testing. Over to the left hand side, we've got the power switch, and we've got a display rate adjust potentiometer here. So if we just put it back to operate, you can see that the display is updating quite fast. Well, you can slow that right down. But I like it just off the indented max position there. I think it gives about 1 a second, something like that. It's not too bad. Next to that's a damping pot, and it does exactly what it says. It's just used to damp the actual readout there. So if I turn it right up, the jumping around that you were seeing there is not going to be as high. But again, I'll just leave that at the far left there, the indented minimum position. Now there is options for this picoammeter. You can get plug-in cards that will allow the output to go to a printer. I don't have those cards, but we'll take a look inside anyway once we've carried out the tests that I'm proposing to do. So sitting above it, I've got my Keithley 225 current source, which I'm going to use to test the 440. So we'll run through some of the ranges, some of the issues we might find along the way before we get to the picoamps, where I'm actually going to bring in my 3458A 8.5 digit multimeter and my 3245A universal source. But for the moment, we're just going to use the 225. So if I wind it round to the milliamps, or the first of the milliamp scales, you can see you've got a DP sitting there. I've got this already set up for 1 milliamp, 1.00 milliamp scale there. It's on standby at the moment. So if I just plug in the BNC there and then select operate mode, you can see that I'm getting exactly, or almost exactly, 1 milliamp there. Perfect. And if I go to the next position, I'll shift the decimal point, 0.997. Again, looking pretty good. But let's go a little bit further. Let's go to a microamp scale. Let's dial in 5 microamps. There we go, pretty good. change the decimal point, spot on, and again, well, overscale. When you overscale the 440, the display does actually go blank. It's only capable of 2000 counts, that's 1999. I've gone beyond that. So let's just adjust the microamps down to 1. Should be able to display that. Yep, spot on, 1 microamp. What about nanoamps? Okay, well, the 225 is capable of that. So let's just select nanoamps. Let's give it 10 nanoamps. .3, slightly off. 10.14, again, slightly off. And you can see there's a slight difference between the 2 nanoamp scales there. And if I just put this down to 1 nanoamp, should be able to get that one there. 1.033. Now, the 225 isn't spot on. I did actually calibrate it this morning actually. Went through the 225 calibration manual and set it up best I can. But what you do have is on the 225 is a fine adjust pot here. So I can actually adjust that fine adjust just to zero that in there. But more of that later on. And finally, what about the picoamp scale? Well, this is not capable of going down into the picoamp scale. Not quite anyway. If I select 0.1 nanoamp, that is actually 100 picoamps. Now as you can see here, it is actually displaying, well, it's quite overscale, 124. And that's a combination of the calibration of the 440 needing done on the picoamp scale, because there's some potentiometers inside. So we'll get in there and have a look at that. But also, we're stretching the limits of the 225 itself. As I said earlier, I do actually have my own 3245A universal source, and it's capable of delivering current. So let's hook it up to the 440. Okay, so I've got the 3245A hooked up right now, and I'm actually delivering 0 microamps at the moment. And as you can see, I'm on the microamp scale here, or one of them anyway, and it's reading 0, no problem at all. So let's just go and raise that to 1 microamp. 1.0 E-6. There we go. And it's pretty well spot on. 0.99. I should be able to go to the next one along. Wow, absolutely perfect. 1 microamp. Well, let's try nanoamps. So 1.0 E-9. That's 1 nanoamp. Put it to the nanoamp scale here. As you can see, it's jumping around a little bit. And that is actually the 3245A. But more about that in a second. So let's try going to the picoamps. Well, if I go 1.0 E-10, that's 0.1 nanoamp, which is 100 picoamps. And you can see it's jumping around quite a lot, and that is actually the 3245A that's delivering that noise. Why is that? Well, here is the datasheet for the 3245A, and down at the bottom here, DC current output. So it's actually got 4 ranges. And I've got it in auto range at the moment, and it's also got a high resolution and a low resolution mode. And obviously I'm in the high resolution mode. So in the 0.1 milliamp range, the resolution is down at 0.1 of a nanoamp. So already we're pushing the 3245A right to its limit. Now I did actually output 0.1 of a nanoamp, but it was jumping around. Well, if you look down here at the DC accuracy on the 0.1 milliamp scale, the accuracy will be 0.0052% plus 3.3 nanoamps in the high resolution mode. And if you plug those figures in to the 0.1 nanoamp output that I set it to, if you factor in the 0.0052% plus 3.3 nanoamps, the actual output can be anywhere between minus 3.2 and plus 3.4 nanoamps. And of course, the output not going to go negative, so let's call the bottom end 0 nanoamps. So it's going to be anywhere between 0 and positive 3.4. Now the noise characteristics of the 3245A, well, we don't really see that's mentioned specifically on the datasheet, but given these figures, I think we can assume that the 3245A is noisy right down at the bottom end there. So I can't use the 3245A to calibrate the picoamp scale of the 440, but I still think we can possibly use the 225. Let me hook the 225 up again. So I've set the 225 to 0.1 nanoamps, that's 100 picoamps, and as you can see, it's a lot more stable as we saw earlier. It's not accurate, but it's stable. So how about I hook up the 225 to my 3458A 8.5 digit multimeter and calibrate the 225 by adjusting the fine adjust pot here so that it's spot on 100 picoamps, and then plug that into the 440. Okay, we'll do that now. And there we go, still got the same 0.1 nanoamp, 100 picoamps into the 3458A. Now as you can see, it's reading quite stable there. So let's adjust the fine control here to get that to read 0.1 of a nanoamp. I think that'll do. And then plug that back in to the 440. And as you can see, it's pretty close. Now it looked like that did the job, but we need to take a look at the datasheet for the 3458A just to make sure everything is as it seems. So here we have the datasheet for the 3458A. We're looking at the DC current section, and under the accuracy heading we've got all the different scales here and the relevant accuracy of those ranges. And against the 100 nanoamp range which we were in, you can see that we've got a figure here, we've got a double figure here. And in brackets here, it's ppm reading plus ppm range. So there's two figures which affect the accuracy of that range and the signal coming into the meter. 10 plus 400 for the ppm reading and ppm range. Now what that is, the first figure is the accuracy of your actual reading. The second figure is a fixed error based on the full scale of the range being used, in this case the 100 nanoamp range, because you can see that the different ranges have different fixed error figures down there in ppms. Now over here I've handwritten, if we had applied 100 nanoamps to the meter, then applying this formula here for the ppms to determine the accuracy, that would give me an accuracy between 100.041 nanoamps and 99.959 nanoamps. So it's pretty close around a 100 nanoamp applied to the 3458A. However, we're wanting to apply 0.1 of a nanoamp, 100 picoamps. Now we've still got to use that scale because there is no picoamp scale or anything below. We're already on the lowest scale of the 3458A. Now since I've applied 0.1 nanoamps, 100 picoamps to the 3458A, then the accuracy is nothing like as close as it would have been for 100 nanoamps. Plug in 0.1 nanoamps into that 10 plus 400 ppm figures, I get a range of anywhere between 0.14 and 0.06 nanoamps. So we can't even use the 3458A to accurately set the calibration of my 225 current source that we can then use to calibrate the 440. Whoa, 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 stop the testing! What's happened? Why is the lid off? Well, it stopped working. I had it fed a 1 milliamp signal from the 225 and I had a nice 1.000 display, and I just happened to glance at it later on and it was reading a completely different number. So I thought, wow, what's going on? So a little bit of investigation off camera and the power supply had gone. One of the rails went a little bit haywire. The minus 24 volt rail went down to about minus 8, something like that. And the other rails weren't exactly accurate. So I had a look at the power supply, decided that one of the capacitors, the electrolytics, looked a little bit suspect. And here it is. Yeah, I'm sad to say this 50-year-old capacitor has seen better days. It's bulging at the bottom there. This one's finally met its maker. So I just took the opportunity to replace all 4 of them. And if you look at the underside there, this one here is looking a bit dark there as well. So they're probably all on their way out. So I've replaced them with some nice Nichicons and the unit's back up and running again. And there's the Nichicons fitted there. There is a couple of other capacitors around that I might take a look at, possibly with a view to replacing, but for now it's back up and running, so I think we'll just leave it at that. And here's where I changed those capacitors, but if you look further up here, somebody's been in here before. You can see some solder flux and what looks like a transistor there. It's possibly been replaced at some point because the legs are just bent down right along the traces, unlike the other components on the board. Now a quick look at the underside. This actually helped me get the unit up and running again, because the schematic for the power supply, actually it's a little bit unreadable, but thankfully you've got a few traces here, or a few pads, plus 3.6, minus 15, plus 15, plus 170. Yep, perfect for doing a little bit of troubleshooting. So let's just check the DC outputs from the power supply. So we'll go on to the plus 15 volt rail here. I better switch it on first. Yeah, 14.9, that's good enough. And the minus 15 volt rail, minus 16.6. That's not right. How about the positive 3.6, which is here? 3.51, yeah, that'll do. And the positive 170, since it's here. Yeah, 187, that's probably good enough. So, we've got a problem with the minus 15 volt rail. Here is the schematic for the power supply. You can see the transformer here, and you've got the plus 15 volt and the minus 15 volt there, and you've got your ground, your 0 volts right along the middle. So the plus 15 volt circuit is along the top and the minus 15 volt along here. So let me zoom in a little bit closer and let's see how the minus 15 volt rail operates. So the heart of the plus 15 volt rail is this Zener diode here, D10, which sets the regulation for the whole of the plus 15 volt rail. I'm not going into detail about that, but you also have an adjustment pot here for adjusting that plus 15 volt rail. And as we saw, the plus 15 volt rail is pretty much spot on. So how does the minus 15 volt rail work? Well, if you look here, we've got 2 resistors. It's actually a voltage divider across the plus 15 and minus 15 volt rail. And they're round about the same values, 7.5k and 7.32k. So that'll give you a virtual 0 volts or thereabout at the base of Q117. Now this is a differential amplifier here, Q117 and Q116. The base of Q116 is tied to the 0 volt rail. So therefore any deviation on the minus 15 volt rail will affect this virtual 0 volt point here on the voltage divider, and that will be reflected on this line here, and quite luckily they've annotated it and it should be sitting at round about minus 0.6 of a volt. Q113 just amplifies that, and then you've got a Darlington setup here consisting of 2 transistors, and that basically series regulates the minus 15 volt rail. So we could have a problem with the voltage divider, or the Q117, Q116 I think it is, and we'll need to check and see if we've got round about minus 0.6 of a volt there, and also check if Q110 and Q111, the Darlington setup's working okay. There is actually another transistor here, Q112, but that's just used to limit the output current. Okay. So first things first, how about that voltage divider? Let's go on to it, and we're looking at about minus 0.5 of a volt. Well, since we're getting minus 16 volts out, it's not much surprising it's biased slightly negative. So I suspect that 2 resistors are okay. Now I do notice there's some flux in and around this area. 2 transistors looked like they've been replaced. Okay, how about the base of Q113, which was annotated to be minus 0.6 volts? Well, that is here. And we're getting minus 0.6 volts. So let me take a step back then. Let's look at that minus 15 volt rail again. And I'm going to check and see what sort of ripple we're getting on it. 0.8 of a volt. I would say that's far too high. How about the plus 15 volt rail? And it's virtually 0 volts. I think we've got a problem with ripple on the minus 15 volt rail, and that's giving me that DC offset there. So let's just check and see if we've got a capacitor somewhere for smoothing that rail. Maybe it's gone as well. Okay, so C111 is the capacitor I'm looking for, and it's underneath the Nixie board. So I'm going to have to remove that one and take a look underneath. So I'll do that now. And luckily the Nixie driver board just unplugs by the looks of things. There's just 3 screws holding it in. Oh, in fact one of the screws is slack. Be very careful with the tubes. There we go. Wow, easy to take out. And there we go. Lovely. And there we go. And we've got 2 electrolytics. This one's the one across the minus 15 volt rail, and this one over here is across the plus 15 volt rail. So I'm just going to remove them both and change them out. And this part here is for adjusting the plus 15 volt rail. Nothing wrong with that. I'm going to leave that intact. Okay, so I've done a little bit of measuring off camera, and as I said, I'm getting a virtual 0 volts or thereabouts on base of Q117, and the differential amplifier seems to be working because I'm getting minus 0.62 volts here. It's supposed to be minus 0.6, so that's near as damn it correct. However, over here we're supposed to get on the collector of Q113, that small amplifier PMP transistor there, I'm supposed to be getting minus 16.3 on the collector. I'm getting minus 23. That's miles out. Now I've double checked I'm not overcurrenting the negative 15 volt rail, because here is a series resistor here that limits the current with that Q112 transistor, and it's specified around about 0.2 volt, and what I think it means there is no more than 0.2 of a volt, and I'm getting 0.13, so that's fine. So the problem seems to be up here. So let's check out Q113 with the power off and see if we can take some readings on that PNP transistor. So So I've got my meter in diode test mode, and if I go on to the base of Q113, here it is here, go into the base, I should get a diode test between the base and the collector and the emitter separately. So let's go on to the emitter, and I'm getting 0.6 of a volt, no problem. Let's go on to the collector, and it's jumping all over the place. I'm way up at 1.56 volts. That should be around about 0.7 of a volt. So I think that transistor there is highly suspect. So I'm going to change it out. And here it is. It's a 2N3638A. Now interestingly, out of circuit, it's absolutely dead. I'm getting no diode drop across any of the pins whatsoever. And the 0.6 of a volt etc. I was measuring was just some other transistors that are connected to it. So I think Q113 is gone. So I'll try and find a replacement from a stock, and we'll put it in and try it out. Okay, so there was 2 transistors gone. This is Q113, which was that amplifier transistor driving the base of the Darlington pair. This is the first transistor in the Darlington pair. It's okay. And this one here, the actual main transistor of the Darlington pair, that one's gone. And looking at the circuit board on the underside, somebody's definitely been in here before, because there was flux all over all 3 of those transistors. In fact, this transistor here, you can see the long legs in it. The legs of the transistor had been bent down along the tracks of the underside because the pads had been ripped slightly. So I think somebody's been in here before trying to attempt to repair and probably couldn't manage, hence the minus 16 volts or so. So how have I fixed it? Well, I removed the 2 transistors there, as you saw, the Darlington pair, and I've just changed them out for 1 transistor, a PNP Darlington transistor, which will cover the function of both of them. So, but I'll put a little heatsink on it just in case. It's only going to drive at just about 200 milliamps anyway. The proof is in the pudding, so let's measure that minus 15 volt rail. So let me put power on. There we go. And the minus 15 volt rail, minus 15.3, perfect. And I'll just double check the plus 15 volt rail, 14.9. Now I did notice that those 2 resistors, the voltage divider, according to the schematics 7.5 and 7.32, but the parts list says both of them are 7.5, and it's 7.5s that are fitted. So I guess there's a little bit of a discrepancy there. But I'm quite happy that the minus 15 volt rail is now working. So here we are inside unit, and as you can see there's a number of different PCBs in here, all which serve a specific function. But straight away you can see the Nixie tubes along the bottom here with the driver board that they're connected to right behind the red Perspex panel on the front there. The main board also has the potentiometers for the calibration of the unit. They're clearly identified, including that 100 picoamp pot here that we're also interested in getting adjusted. You've also got the range selection switch here, and connected to it is a small PCB. And very interestingly, there's a number of high resistance resistors on it. There's a couple of glass-filled 100 gigaohm resistors there. Obviously glass-filled to stop a humidity or moisture problem changing the resistance, but don't get your fingers anywhere near there because fingerprints can affect the resistance. You've also got a couple of other resistors there, some slightly smaller brothers, a 100 mega ohm and a 10 mega ohm down there. Now effectively what the range selection switch is doing is just varying the gain on an amplifier stage close to the input of the 440. It's as simple as that. There's no large complicated network of resistors necessary. It's just a gain adjust stage. Over at the left hand side, we've got the polarity PCB. That's the one that gives you that plus or minus indication on the front of the unit. Next to that, you've got the 1000 PCB, it's called, and that just has that single indicator on the front of the unit for the thousands digit display. Now over here we've got an oscillator PCB consisting of a 100 kilohertz crystal, and that's necessary for the dual slope A to D operation of the unit. And next to that is the all important integrator PCB. And over in the corner here, this is the input board. And you can see the actual input along here, raised off the board with, I'm assuming, some Teflon standoffs. Looks like we've got a resistor in series and into the board itself. And interestingly, and speaking to an engineer at Keithley, or Tektronix, they're telling me that this input board here is shared, if it's not very similar to, the input board on the Keithley 610C, the electrometer. And it was also told that the 440 along with the 445 were perhaps the very first instruments that Keithley made with Nixie tubes, even before the Model 160 digital multimeter. Now if I look a little bit closer, you can see there is some date stamps in some of these ICs. I've got 35th week 74 and there's a 49th week 73 just underneath this metal bracket here. So we're talking 1973 anyway. And here's the block diagram for the A to D section, and down at the bottom left here we've got a dual slope integrator, which is the heart of the A to D converter. So the analog input is connected to the integrator for one complete line frequency cycle, after which the analog signal is removed by turning off this FET, and the signal to the integrator is then replaced with the signal from the discharge reference. And what that does is it starts to ramp down the integrator until such time it crosses the 0 point. And the time it takes for it to ramp down is proportional to the original value presented at the input. Because obviously the higher the voltage at the input, the longer it's going to take for it to ramp back down. And it's that time that is then measured and presented to the Nixie tubes via this part of the circuit here, which then drives the Nixie tubes, as you can see here, and also outputs a BCD signal for the optional interface on the rear of the unit. Now, what I did actually find when I was looking at the documentation is reference to a 445, this being the 440, and I'm not too sure what extra functionality the 445 has got. But certainly the schematics seem to indicate there is some additional functions. Be great to find out what the 445 does. Well, I've just managed to come across a plan B, or maybe it's a plan C. I've just managed to acquire, cheap off of eBay, a Keithley 486 picoammeter. Now this thing can go down to the picoamps. So I've hooked it up to the current source here. I'm currently outputting 0.1 of a nanoamp, that's 100 picoamps, into the picoammeter, and I'm going to use that as a transfer standard for the 225 driving the 440. And the picoammeter here, the 486, is much more within its range from the 0.1 or 100 picoamps that the 225 is putting out. In fact, I've got it connected now, and as you can see, 0.124 nanoamps. That's 124 picoamps. More or less guaranteed. So actual fact, the 3458 wasn't that far off, given that we were way outside the spec of a 3458A. So now that I know I'm outputting 124 picoamps from the 225, I can quite simply connect that to the 440 now and adjust the internal potentiometer if required. So let's plug it in and see what we get. and it's only slightly out. So let me just take the lid off and we'll tweak that picoamp pot inside. Right, here's a picoamp pot here. So let me just tweak that to 124. There we go. I think that'll do nicely. Well, that's it, I think, for the 440. A lot of unexpected things to deal with along the way, but it was extremely fun. So, thanks for watching, and remember, you can always comment down below, and don't forget to like and subscribe. It really does help the channel grow. There's plenty more repair videos on my channel, from the simple to the complex. Check them out, and thanks for watching.